Hello everyone, and a very warm welcome to all of you tuning in. Before we dive into one of the most fascinating quirks of the quantum world, I want to take a moment to send my very best wishes to you and your loved ones. Wherever you are, I truly hope you are happy, healthy, and in good spirits. Let's jump in. Imagine you have a cup of coffee. You can stir it with a spoon, you can see it slosh around when you walk, and most importantly, if you tip the cup over, it spills everywhere. This behavior is something we are so familiar with that we never even question it. The thickness of a liquid, its resistance to flow, is what scientists call viscosity. Now, picture a liquid that has absolutely zero viscosity. A liquid that can never be stirred, that has no friction at all, not even within itself. A liquid that can defy gravity and silently creep up the walls of its container, leap over the top, and escape, seemingly of its own accord. This isn't science fiction. This is the reality of superfluid helium, one of the most bizarre and mesmerizing substances ever discovered. To understand how this is possible, we need to take a little journey into the heart of the atom, specifically the atom of helium. You might know helium as that light, inert gas that fills party balloons and makes your voice sound squeaky. Helium is a real individualist in the periodic table. It's a noble gas, meaning it doesn't like to react with other elements, and it has the lowest boiling point of any element. But to witness its most incredible trick, we need to make it incredibly, almost impossibly cold. We are talking about temperatures only a few degrees above the coldest temperature possible in the universe, absolute zero. Absolute zero is the point where all molecular motion theoretically stops, and it is measured at minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. It's the ultimate cold. Now, ordinary liquid helium exists at temperatures just a few degrees above this point. But when you cool liquid helium down even further, to about minus 271 degrees Celsius, or just 2 degrees above absolute zero, something magical happens. It undergoes a dramatic transformation, a phase change like freezing or boiling, but into a completely new state of matter known as a superfluid. Scientists call this transition point the lambda point. At this temperature, the helium atoms lose their individuality and begin to act as one single, coordinated entity. This happens because of a quantum mechanical effect called Bose-Einstein condensation. Without getting too deep into the complex physics, this means that all the atoms fall into the exact same quantum state. They stop behaving like a crowd of individual people and start moving in perfect, lockstep unison, like a perfectly synchronized dance troupe that has become a single, flowing superatom. This unity is the source of the superfluid's incredible powers. Because all the atoms are moving together, there is no friction between them. The viscosity doesn't just get very low, it completely vanishes. It becomes zero. This lack of internal friction leads to behavior that looks like it's breaking the laws of physics as we know them. If you were to try to stir a cup of superfluid helium with a spoon, you would find no resistance at all. The liquid would not swirl. In fact, the spoon would move through the liquid as if it weren't even there, because the superfluid simply cannot be stirred. It's a liquid that has become the ultimate pacifist. It offers no fight, no friction, nothing. This brings us to its most famous party trick, climbing walls and escaping containers. This mind-boggling phenomenon is due to a property called film flow. The helium atoms are so devoid of friction and so desperate to find a state of equilibrium, to spread out their energy, that they are pulled by a force known as the van der Waals force. This is a very weak force of attraction between molecules and the atoms of a surface. For any normal liquid, this force is far too weak to overcome the liquid's own viscosity and surface tension. It's like a person trying to climb a perfectly smooth glass wall. They just can't get a grip. But for superfluid helium, which has zero viscosity and therefore no internal grip to overcome, this tiny van der Waals force is more than enough. The helium atoms form an incredibly thin film, just a few hundred atoms thick, on the surface of any material it touches. And this film begins to flow. It doesn't matter if the surface is vertical or even upside down, the superfluid helium will creep up and over the edge of its container. Once it gets over the top, it will continue to flow down the outside until it drips off the bottom, effectively emptying the container one atom-thick layer at a time. It's like the liquid has decided it wants out and has found a way to walk out on its own. The strangeness doesn't stop there. If you were to place a superfluid helium in a container with a very fine porous filter, something that would completely hold back any normal liquid, the superfluid would flow through the tiny pores without any hesitation or pressure drop. It's as if the pores don't even exist to it. This again is because of its zero viscosity. There is nothing to slow it down or clog it up. This property makes it the perfect quantum solvent. Furthermore, if you were to set up a circular channel filled with superfluid helium and get it moving, it would never stop. In a normal liquid, friction would eventually slow the flow and bring it to a halt. But with no friction, the superfluid can, in theory, flow forever. It's the closest thing we have to a perpetual motion machine in nature. Perhaps one of the most visually striking demonstrations of its weirdness is the fountain effect. If you take a thin tube packed with a fine powder and shine a light on it to warm the very tip ever so slightly, the superfluid helium will rush up the tube and spray out like a fountain. Normal liquids move away from heat, but the superfluid, in its quest to equalize its unique energy state, is drawn toward the warmer area, creating this beautiful and counterintuitive quantum fountain. All of these bizarre properties are not just laboratory curiosities, they are vital for real-world applications. Superfluid helium is used to cool the massive superconducting magnets in MRI machines in hospitals and in particle accelerators like the Large Hadron Collider. Its incredible thermal conductivity, another property of its frictionless flow, allows it to carry away massive amounts of heat with minuscule temperature differences, which is absolutely essential for keeping these complex machines at their ultra-cold operating temperatures. So, the next time someone you know gets an MRI scan, you can think about the fact that a tiny amount of this miraculous, wall-climbing liquid is playing a huge role in their healthcare. In the end, superfluid helium is a stunning and beautiful reminder that the universe, especially at the smallest scales, operates on rules that are utterly different from our everyday experience. It is a direct window into the quantum world, a world usually hidden from our view, made visible in a dancing liquid that defies gravity and flows without end. It shows us that even something as simple and familiar as a liquid can hold profound secrets, waiting for us to get just cold enough to discover them. It is a true marvel of physics, a whisper from the quantum realm that we are fortunate enough to be able to see with our own eyes.